pile like this in winter days, the heat that is generated during the conversion of biomass into compost causes the water in the pile to evaporate. That water vapor is what you see as steam coming from the compost pile. The evaporated water takes a lot of energy with it, and in fact, this way of evaporative cooling is one of the most efficient ways for removing heat. But note that if the water is removed from the pile and it's not replaced, the pile will dry out. In this video, you will learn how to calculate how much air you need to supply to remove the heat of a reaction, but you will also learn to calculate how much fresh water needs to be added to compensate for the loss of water due to the evaporation. The composting of biomass could also be done in a container like this. In the container, the microorganisms convert the biomass aerobically, and this generates a lot of heat. That heat should be removed by cooling, otherwise the composting stops because the microorganism stops functioning. So we bring in a flow of dry, cold air in contact with the compost. The water inside the compost evaporates, and the water vapor leaves the container via the outflow of the air. If we do not compensate for the loss of water, the composting reaction will quickly stop because the microbial community needs the water to survive. So we need to add fresh water too. Not too much, otherwise the oxygen supply to these microorganisms becomes limiting, and this will also stop the composting. But how much cool air and cool water needs to be added? To determine how much cooling air is needed and how much fresh water should be supplied, we must set up an overall enthalpy balance. To set up the balance, we'll start with the incoming enthalpies, which are the enthalpies of the fresh water and of the fresh air. Leaving the container is the enthalpy of the air with the water vapor. And also the total enthalpy of the reaction is included in the enthalpy balance. We want to determine the flows of water and air, and to do so, we need to find the values of the other parameters. You already learned how to determine the reaction enthalpy and how to determine the specific enthalpies of the inflowing water, HW in, and the air, H air in, if the temperature of those streams, of course, are provided. But the outgoing air flow contains water vapor and air, and the mole fraction of the water vapor, the YW out, that's still an unknown. We can find the latter by realizing that the water vapor pressure, IW out times PT, at the outlet is probably close or equal to the saturation pressure of water. This PW set can be calculated using Antoine's equation of water vapor pressure at a given temperature. In this case, we choose the maximum temperature that the microorganisms in the compost pile can handle. With the value of this water, mole fraction of water in the outgoing gas, we can calculate the specific enthalpy of the outflowing air. But the enthalpy balance still has three unknowns. The unknown flows FW in, the air going in, and the air leaving. So we need more equations to solve this balance. Let us set up the steady state balance for the air. The air enters as fresh air with a flow FA in, and it leaves with a flow of the total flow times 1 minus the mole fraction of water in that flow. The last equation we need is the water mass balance. The water that comes in, FW in, and leaves with the vapor, so YW out times the flow of the air out. Let's see what we got. I assume we know the composition and the temperatures of the flow. So the specific enthalpies of the different flows in the enthalpy balance can be calculated. We also know the reaction kinetics. The liquid volume in the tank is determined from the mass balance of the reactant and the known reaction kinetics. Then we have the heat of the reaction. Well, that's calculated from the reaction stoichiometry and the heat of combustion of the reactants and products in the reaction. We want to calculate the incoming flow of air and the incoming flow of water, so therefore we first need to determine the enthalpy and flow of the outgoing air. This humid airflow consists of both water, vapor and air. This means that the enthalpy of the outgoing air is equal to the enthalpy associated with the water vapor and the enthalpy associated with the air. We have Antoine's equation, we have the water balance and the air balance. So we got 5 equations with 5 unknowns. And 5 equations, 5 unknowns, that means we can solve those equations. And this will tell us how much airflow is needed for cooling and how much water needs to be added to prevent the drying out. Of course, the composting was just an example. The evaporative cooling is applied in all kinds of situations. So if you for instance look at what's happening in your fridge at home, the cold cooling liquid enters and absorbs the heat from the air in the fridge, chilling the inside of the fridge. This turns the liquid into vapor, so the liquid cooling fluid enters but leaves in a vapor phase. By setting up associated enthalpy and mass balances, you will be able to design the heat exchange equipment needed to take away the heat generated in your reaction.